Hello everybody, I'm Lavanya, a research scholar at IIT Madras, and I'll be doing live interaction sessions for the NPTEL course Principles of Downstream Techniques in Bioprocess. So today we'll be looking into the introductory session or the preparatory preliminary assignment that's been given on week 0. And further weeks we'll be having an interactive session every week at on Friday between 6 and 7 p.m. Hello everybody, I'm Lavanya and Hello everybody, I'm Lavanya, a research scholar at IIT Madras, working in the Department of Biotechnology in Protein Biophysics Lab. So I will be assisting in carrying out the interactive sessions for the NPTEL course Principles of Downstream Techniques in Bioprocess. So today we'll be looking into the introductory session or the week 0, where we will be looking into the solutions of the preliminary assignment before we get into the actual course. So this is a 12-week course and we'll be meeting every Friday between 6 and 7 p.m. And I hope you all got the link. So let's get started. So today it's going to be more of a basic peek into what this course is going to look like, and there's we're not going to get into details too much. Let's get into the first question. Which is an instrument used for measuring pressure differences? Is it barometer, manometer, sphygmomanometer, or none of the above? So usually this course will have the audience and we will be taking some sort of a poll or use the chat box for answer. Today, since it's an online recorded version, I'm going to just go ahead with the answers, but let me give you a few seconds for each questions to think what the answer could be. So is it barometer, manometer, sphygmomanometer, or none of the above? The answer is manometer. Of course, barometer is used to measure the pressure difference, but pressure, atmospheric pressure maybe, but not a difference. Similarly, sphygmomanometer is used to measure the blood pressure in humans, but the right answer is manometer, where you can actually measure the difference. You can either expose this a tube-like structure having a heavy liquid, and this tube will have a differing heights in whenever there is a pressure difference. The liquid inside the tube will have different heights on each arm. So it can either be exposed to the atmospheric pressure, where you measure the difference or the pressure inside this particular region with reference to the atmospheric pressure, or it can also be attached to a tube, a long continuous tube or column of fluid, where it can give you the pressure difference between those two different points in the pipe. Okay. The second question is, in the case of size exclusion chromatography, which type of molecule will come out first? Let's take 5 seconds to think about the answer. You can also pause and think about it and then play. So option A is large, B is small, C medium, and D does not depend on size. So right there we have a red herring, because the question is size exclusion chromatography. So obviously it has to depend on size. So option D is wrong right away. So next you have to think about A, B, and C. Since it's size dependent, obviously medium is not going to come out first. It has to be either large or small. So A or B, which is it? Let's look into the answer. So size exclusion chromatography works in the principle of having beads of a specific polymer which has a cutoff of pore size. So when you're having a solution or a mixture going into the column, it is composed of different molecules of different sizes. So the larger molecules cannot enter into the pores of these beads or the gel permeation chromatography. So these gel beads will not be able to take in the molecules that are bigger than the pore size. So these red molecules that are big, that look bigger, are going to pass through the interstitial space between the void volume between the beads and going to come out through the column first, followed by the next set of molecules which have a smaller size than the red ones are going to pass through the column and come out next. And finally, the smaller molecules, or in this case, the smallest ones, are going to pass through the pores and then come out of the beads and then will elute last. So, the principle of this mechanism is to create some time difference between all the molecules in a solution. So, the answer is the large molecules will come out first. Third question. Fick's first law of diffusion is dash, where Ja is the molar flux, uh, L is the length, dV is the concentration gradient. This is a straightforward question where you just need to know the formula of Fick's law. Let's look into the right answer right away. So, Fick's first law of diffusion states that the flux or the mass flux in the solute is directly proportional to the diffusion coefficient, directly proportional to the concentration gradient, and the constant here is the diffusion coefficient. You can This constant is still dependent upon the temperature, pressure, and all other environmental factors. However, it is predominantly dependent on the concentration gradient, and you have a negative sign here simply because diffusion happens from higher to lower concentration rather than lower to higher. Therefore, you have the negative sign here. It shows that there is a directional movement from higher to lower concentration. Fourth question. Arrhenius rate constant is dash. A is the pre-exponential factor, R is the gas constant, E is the volume, T is the temperature, and E is the activation energy. Again, it's a straightforward question. I hope most of you would be aware or familiar with the Arrhenius equation. Let's take 5 seconds. Pay attention to the denominators as well as the sign. Okay, the answer is A. K is equal to A e power minus Ea by RT, where K is the rate constant, A is the pre-exponential factor or Arrhenius constant, and E is the base natural logarithm. Minus EA. EA is the activation energy, and RT, gas constant, and temperature in Kelvin fall in the denominator. So you do not have negative sign here or B here, and you do have a negative sign before EA. Right, let's go on to the fifth question. Hydrophobic interaction plays an important role in adsorption chromatography, affinity chromatography, reverse phase chromatography, or ion exchange chromatography. Let me just stay in the call. I think since we do not have any participants here, let's continue. Hydrophobic interaction plays an important role in is it adsorption, affinity, reverse phase, or an exchange chromatography? Think about it. So adsorption is based on the chemical principle of adsorption. So you do not have necessarily need hydrophobic interaction there. Affinity chromatography can be due to hydrophobic, but it is even more specific and is not excluded to hydrophobic interactions alone. Ion exchange chromatography, as it suggests, is based on the ionic charges that is present in the species. Therefore, reverse phase chromatography is the right answer. where the stationary phase is hydrophobic in nature and the mobile phase is polar. And based on the hydrophobic, how hydrophobic the solute molecules are, they separate out. Question 6. The pH of solution A is 6 and that of solution B is 3. Then the concentration of H plus in solution A is, you will have to work this out with a piece of paper. You can pause the video and do that. Let's look into the answer now. So remember that pH is the negative logarithm of H plus ion concentrations. So for solution A, I'm denoting with subscripts A everywhere and for B with B. So pH A is negative logarithmic concentration of H plus ions in A, and pH for solution B is negative logarithmic of log of H plus concentration in B. So we know that pH in of A is 6 and that of B is 3. So I'm equating that here and substituting that here and continuing with the equation. Now I'm shifting the log to the other side and raising it to the base of 10. So we have H plus concentration in A is 10 power minus 6 and H plus concentration in B is 10 power minus 3. We know that 10 power minus 6 is 1000 times smaller than 10 power minus 3. Therefore, pH of solution A is 1000 times less than that of B. I hope that was clear. Question 7. The enzyme that catalyzes the reaction A to B, which is reversible in both directions, changes the heat of reaction, equilibrium constant, entropy of the reaction, and rate of both forward and backward reaction. Let's take 5 seconds. Please think about what an enzyme actually does in a reaction. Alright, so the primary use of enzymes is to increase the rate of reaction, decrease the activation energy so that the rate of the reaction is increased. But since this is a reversible reaction, the rate of both the forward as well as backward reaction is going to be increased. Uh, that is the parameter that's going to be changed in all of the options here. There was the answer. Question 8. NSAIDSR. Again, this is a straightforward question. You just have to expand what NSAIDS is. If you're already familiar with it, you will be able to eliminate all of the options and arrive at option A, which is the right answer. Non-steroidal anti-inflammatory drugs. NSAIDs stands for non-steroidal anti-inflammatory drugs. Therefore, A is the right answer. I've given some of the examples here. Question 9. The maximum number of hydrogen bonds that one water molecule can form are. So remember that H2O has 2 H and 1 O, and oxygen has a lone pair of electrons which can interact. If you take a piece of paper and work this out, you can see that the water molecule in the center has 2 H and a single O in the center, and it's able to interact with 4 other water molecules. So the number of hydrogen bonds that it can form are 4. The input feed to a fresh packed bed absorber is shown. X-axis time and y-axis concentration of the solute. However, we do not know where the time 0 is. How will the output concentration appear? Choose one from the following list. Here I'm assuming that this flow has already begun and this is the feed that is being input into this packed bed absorber. So think what the options could be. You can straight away eliminate B because this is not going to happen. Also D. And C again because there's a constant field and there's no reason for it to decrease after some time. So B, C, D and are removed. A, E, and F seem probable, but in a packed bed absorber, it is more logical to expect E or F rather than A if you look at how the curve progresses over time. Because you generally have a lag when the solute has still not reached. If this is an empty column or if this has a different buffer or solute or does not have any solute at all, and you are suddenly introducing an input feed which contains this particular concentration, then it would lag for some time, and slowly the input would come out of the stream because you're going to have the detector right here. So initially, for some part of the column, there will be nothing, and then that gets the liquid there gets pushed out, and the new feed gets in. So you will have a lag and a slow rise in concentration, which then stabilizes after some time. So the most probable solutions are E or F. But since here we do not have any T0, or we don't know what the column already has, so this has been the input feed for a long time, we will be going with option F, which is most safe. So I would say that E and F are the most probable solutions for this, depending on what time it is or what this column is already equilibrated with or is having inside before the speed is input. So I'm going with F. So that's it for this particular assignment, which we had non-graded week zero assignment, a prerequisite one before our 12-week program starts. I hope I'll meet you all every Friday between 6 and 7 p.m. for the upcoming 12 weeks. Thank you all.